So next we're going to talk about some of the laws that govern electromagnetic radiation. So the very first one we have is Coulomb's law, which has to do with kind of the basic understanding of electricity, the fact that like charges will repel and unlike charges will attract. So electrons are going to be more likely to be attracted to protons or areas of lesser electrons. Electrons are going to repel each other. So when you have areas of high concentration of electrons, they're not going to want to stay in that location, and that's part of our voltage, right? That potential work. So that gets amplified, the charges and the repulsion or the attraction gets amplified by increasing the magnitude of the charges or decreasing the distance between the objects. So if we move the concentration of electrons and protons further away from each other, that is going to make it harder for them to attract. As we move them closer, that would make it more likely that they'll attract. And same reverse, if we had two electrons close to each other, that's going to really affect the magnitude of that. Ohm's law, mentioned this already, so this is the idea that within circuits, we have the fact that current flows, so again our I, the amperage, current has to flow within the circuit from a negative pole to a positive pole. As it moves through that circuit, it has to deal with the voltage, which is that potential work. So what is the tendency for these electrons to want to flow, as well as the amount of resistance that it has to go through. And so circuits with high voltage can still have a low current. So if we have a high voltage, we can actually still get a low current if the resistance is high. And that's what these various equations mean. So when we get a higher potential difference between the poles, that would then be affected by the current and the resistance as well. So that potential difference, again, that voltage is the potential difference between the two poles. And so it measures the tendency for the current to flow and the potential for work within the electric current. So current flow, I, is directly proportional to voltage. So if voltage increases, current will also increase, but inversely proportional to resistance. So if resistance increases, the current will decrease, the amperage will decrease. Lots of factors can affect resistance. So we're going to see these on the next slide. So things like the material that make up the circuit. So the material that makes up the wire or the connection, the length of that circuit, the temperature of it, and the cross-sectional area. So here's just from your book. So again, you have those 4 reasons, the 4 things that would determine a resistance. So the material, what makes up the resistors and the conductors. So basically how many electrons are kind of free to be able to move. If there aren't a lot of free electrons, it's going to be harder for the current to move through. So an example here is blood and nerves have more free electrons than skin and bone does. So the current's going to want to move through those more easily. The length of the circuit, so the proportional relationship between the length of the circuit and the resistance. The longer the circuit, the more those electrons are going to have to move, and so it's going to be harder for the current to flow. And then vice versa, so the shorter that distance that the electron has to travel, the less resistance that will be there. So we see this again in the body, so examples are seen at a lower output intensity if the electrodes are placed closer to each other rather than further apart. So we don't need as much intensity to move the current if they're closer together. So we tend to stimulate superficial tissues sooner and faster than we would deeper tissues. The cross-sectional area, so the diameter essentially of the material, and so of the wire or the part of the tissue that the current is going to flow through. The greater the cross-sectional area, the less resistance that there will be. So think about this as a garden hose, right, with water flowing through. The greater the cross-sectional area, the larger that opening, the easier the water flows through. If you put your thumb over the opening and shorten that diameter, that cross-sectional area, the water comes squirting out much harder, and you feel that against your thumb. And that's because you've shortened that cross-sectional area. So this helps explain how electrical current can select certain nerves. So remember, we talked about having larger diameter nerves and smaller diameter nerves. The sensory nerves tend to be stimulated before our motor nerves because they have a larger diameter. So they're going to be more apt to take on this current. And then the temperature of the circuit. So as we increase temperature of the circuit, we decrease the resistance to flow. So in the body, if body temperature is high, we potentially have more tendency for the electrons to flow. But that, when you're talking about the body level, it's not as clear in the research because your body can absorb heat and have places called like heat sinks, like your core and other places. So the temperature of the tissue itself doesn't seem to play too much of a role in modalities of E-stim. Our next law, we have the Arndt-Schultz principle, and this is that energy must be absorbed at a level sufficient to stimulate a physiological response. So if we don't have enough energy absorbed in the tissue, we're not going to get any reaction. And if we have too great, we're going to have damage. And so our job then becomes the ability to balance that. We don't want to jack up intensities and our other parameters just because we can, because there's potentially that risk of damage. But we do have to make sure we're actually getting the physiological response that we want so that we have enough energy going to the cells. And then the law of Grothus-Draper, which says that the greater the amount of energy absorbed by superficial tissues, the less that remains to be transmitted to other tissues. And that just makes sense, right? If we absorb more of the energy, less energy is going to be available to go deeper. And so this has to do with the frequency of the modalities. Lower frequency modalities usually have increased transmission rates, and they can go a little deeper. Higher frequency ones usually have more absorption rates because their impedance isn't as great. Cosine law. The radiant energy is more easily transmitted to deeper tissues if the course of that radiation is at a right angle to the area being treated. So when we talk about putting pads in place and getting them to the skin, we want them in complete direct contact with the skin, because as the electricity flows through that electron, we want it coming into the skin and into the tissue at a right angle whenever possible. And then the inverse square law. So the intensity of energy is proportional to the square of the distance from the source. So as we get further away from the source, so in this case maybe the electrode on the body, we're going to have a decrease in the intensity of the energy.